Hi, this Ed puzzle is going over um, the stoichiometry lab that you did, and we're checking to see how well you interpreted the data. So the first thing that we are looking at is what was the mass of that beaker. Now you have your own mass if you conducted the lab in class, but we can see the mass of beaker A for the virtual kids was 82.3. All right. With beaker A still on the balance, you added 10 grams of baking soda. It didn't have to be exact because we were going to do some stoichiometry with that. And so you can see that the beaker and the baking soda came to 91.8. And so if we want to know the mass of our baking soda, we're simply going to take the quantity in line 2, right? And we are going to subtract the quantity that's on line 1. And that, again, if you did this in person, then that is going to be different for you, but it should be line 2 minus line 1, giving you a value. And in our case, that is 9.5 grams. All right. So then we go back to the lab, and now we have some baking soda in beaker A, right? And so if we think through that, we have a beaker, we have some solid in it, right? And then we had to record another beaker, right? And we'll make that beaker red. And in that beaker, right, we found the mass of that beaker, and then we placed about 50 grams worth of hydrochloric acid on that in that beaker. Now, what's important to know is that 50 grams of hydrochloric acid is not just hydrochloric acid. It is hydrochloric acid and water. And because hydrochloric acid is a gas and water is a liquid, and in order to make this hydrochloric acid solution, this acid has been dissolved in our water. And so if we look back to the data, right, we have that mass of the beaker when it was empty, and then we have the mass of the beaker with the hydrochloric acid in it. It didn't have to be exactly 50 grams again. And then what we did, we go back to the directions. It says to perform the reaction, right? And so we slowly added this, right, the red beaker to the blue beaker, and in small quantities. And when we were done, when it stopped fizzing, right, when it stopped fizzing, that's when we stopped adding acid. So the acid level will have gone down, right? It was at this point, and maybe you added enough so that it comes to this point. And so we use some of the acid, not all of the acid, right? And so we go back to our data, and we have the mass of beaker B with the hydrochloric acid that was never added to beaker A, and we're going to compare that to the amount of hydrochloric acid we had originally. And so what we're basically doing here is we are taking line 5 and we're going to subtract line 6, right? And so we're going to take line 5 and we're going to subtract line 6, and that will give us the quantity that we should see here in line 7. And for the virtual kids using Luke Kroner's data, then you would find that it was 26.9. But if you were, if you did it in class, then you would find your own value. All right, so then we look at the mass of the beaker after the reaction took place. And if we want the mass of the products after the reaction, we have to consider, right, what is the mass of the beaker now and what is the mass of the beaker itself? Because everything inside that is our products. Now, those products might be some excess reactants, but from a conservation of mass standpoint, we're not going to be concerned with that. So what we're essentially doing, right, is we're going to take the mass of the beaker and all the contents, right? So this is after the reaction took place. You had the acid and the base, right? We added HCl to NaHCO3. And then what ends up happening is we make water, we make salt, and we make carbon dioxide, right? And so if I want the mass of the product, I'm just going to take line 8 and I'm going to subtract line 1. We're going to take the mass of the beaker with all the products in it and maybe some excess reactants, but again, we're not concerned with that. And we're going to subtract the mass of the beaker. Now, if we do that, we find that value to be 35.1 grams. Now we want to go back and we want to compare this mass of product to the mass of the reactants, because our conservation of mass law says whatever the mass of these two together will equate to the mass of all of these, right? And so we look at the mass of our baking soda. Think about what line represents the mass of the baking soda. And we're going to add to that the mass of the hydrochloric acid that reacted, right? And that will give us the mass of them together. And so in this case, right, that's basically line item 3 plus line item 7. And if we do that appropriately, then we will get 36.4 grams. So if the reactants have a mass of 36.4 and everything at the end of the reaction has a mass of 35.1, we know what the mass of the carbon dioxide was, because the carbon dioxide does not stay in the container. The carbon dioxide goes into the atmosphere, right? And so the difference between these two masses represents the mass of the carbon dioxide. All right, so what are our reactants in this lab? As we said, it's the acid that we combined with the sodium hydrogen carbonate, also known as baking soda. And what are the products in this reaction? Well, that's our water. That's our sodium chloride. You basically made salt water, and that is our carbon dioxide. All right, so then we're supposed to look at how much, if the baking soda is the limiting reactant, then how much carbon dioxide should we have made? And so we're going to go back and grab that 9.5 grams of baking soda. And we're going to perform a stoichiometry problem in order to find the theoretical mass of carbon dioxide that should have formed. So we go from grams to moles first. We're basically going from grams to moles to moles to grams. And in order to do that, we know that our mole to mole ratio step requires that's right, a balanced equation. So in this case, we have HCl reacting with baking soda to form salt, water, and carbon dioxide. And it's already balanced, so now we know the mole to mole ratio. So if we want to go from grams to moles, right, then we're using what's called the molar mass. And if we take the mass of 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens, we would find the total mass of all of those atoms together is 84.0 grams. So whenever we're going from grams to moles, whatever we were given the mass of, that is what we need to divide. It's that specific substance's molar mass that must be divided into that given mass. All right, then we go to our balanced equation, right? That balanced equation tells us the ratio of the sodium hydrogen carbonate to the carbon dioxide. And we look at those coefficients in the front of those symbols. and it's 1 mole of one mole of baking soda is producing 1 mole of CO2. And as we said, though, we wanted the theoretical yield, which is the mass of CO2 we should have made in lab. And what we see is for every 1 mole of CO2, if we want to go from moles to grams, we have to find the mass of CO2, the mass of 1 mole. That's 1 carbon plus 2 oxygens, which happens to have a mass of 44.0 grams. And that, when we simplify, which is basically 9.5 divided by 84 multiplied by 44.0, that will give us 4.98 grams of carbon dioxide that should have been made. Now, if we go back and we look at how much we actually made, 1.3 grams is significantly different. So maybe this isn't our limiting reactant. We're going to have to look. All right. But what you were also supposed to do is figure out whether it was the hydrochloric acid that limited the amount of carbon dioxide that was made. And so in the directions, if we go back, because this was the common problem, in the directions, it said, because we haven't quite learned this information yet, but in order to calculate the mass of carbon dioxide expected from the acid, I asked you to take the 1.0 molar, which is the concentration the acid we used in lab, and you were going to multiply it by the volume of acid in milliliters that you actually reacted. And for this set of data, it was 26.9 milliliters. But then I asked you to divide all that by 1,000. And the reason is we needed to convert our milliliters into liters. And so if we crunch those numbers, we find that we had 0.0269 moles of HCl. That's how many moles of HCl were in that 26.9 milliliters. All right, so if I have our moles of HCl, right, and I'm trying to get to grams of carbon dioxide, I am taking moles of HCl. I'm going to convert it into moles of carbon dioxide and then grams of carbon dioxide. So notice we're missing that first step that we had to do with the baking soda because we're already in moles of HCl. So what do we do when we're going from moles of one thing to moles of the other? We use our balanced equation and use the mole ratio. For every 1 mole of HCl, we will make 1 mole of carbon dioxide. And for every 1 mole of carbon dioxide, what's its molar mass? Well, that's the mass of the 1 carbon, 2 oxygens, which happens to be 44.0 grams. And so if we simplify this, we can see that our HCl was only enough to produce 1.18 grams of carbon dioxide. So if that's the case, look, we can make way more carbon dioxide with the baking soda than the hydrochloric acid. So the hydrochloric acid was our limiting reactant. It produced less CO2, and therefore that's the most CO2 we could have made. And that means we had plenty of baking soda. Some of you might even notice that it dissolves in the water, but so what is the percent yield? Remember that percent yield is actual, right? How much, our actual amount of CO2 made in the lab versus theoretically how much CO2 we should have made in the lab. So what we see here, and then we multiply that by 100 to turn it into a percent. So in this case, we actually made in lab 1.3 grams of CO2 when we should have made only 1.18 grams. Now you're going to see, oops, I have a equals, I should have a multiply. what you're going to find is this is larger than 100%. So something went wrong. You cannot create more CO2 than you theoretically should make. And so somehow we lost some mass along the way. Perhaps our acid was more concentrated than the 1.0 molar, which is probably the most likely reason for this error. And if we actually had more HCl, then we would make more CO2 like we see here. What's our percent error? Well, you could always compare it to 100, but again, percent error is theoretical minus actual divided by theoretical times 100. So in this case, I was supposed to make 1.3 grams. I'm sorry, I wasn't supposed to. I actually made 1.3 grams. I was supposed to make 1.18 grams, and I'm going to divide by the amount I was supposed to make, right? Multiply that by 100, and you're going to see that's 10%, which makes sense. We had 110% yield. We're only supposed to have 100% yield at most, and therefore that extra 10% is our error. All right. Mass cannot be created or destroyed during a reaction. Does this apply to this lab? It applies to any lab. Yes. Yes, it does, right? So why didn't we see the mass of our baking soda and our acid equate to the mass of our products, right? So if we take and we think about it, right? We made salt, we made water, and we made CO2, right? And together, these two together had a mass of 36.4, right, grams. So that means all of this should have a mass of 36.4 grams. But that CO2 bubbled out of the beaker. And so when you massed it after the reaction, right, we were really only massing that salt and water, which was 35.1 grams. So the difference, right, that difference between what we should have massed and what we actually massed would be the CO2. And that 1.3 grams, right, is what we probably made. And that's because we know we should end up with 36.4 grams overall.